Welcome to this next lecture on acoustics. We were looking at the problem of a pulsating sphere, using the Neumann Green function, and we arrived at this point. The solution is almost there, you can see here. It is only a function of r dash, it is independent of the angles theta dash and phi dash. So let us see, we are here now and trying to expand h0 and h0 dash to get the final expression. So h0 dash of Ka looks like this. So let us see over here. We have now P at r dash theta dash phi dash given by minus I rho c u0 into h0 kr dash, which is e to the power of minus I kr dash by minus I kr dash, and in the denominator this expression. So we have to invert this. So if we do that, what do we get? We get e to the power of minus I ka minus I into 1 plus I ka so the numerator has come here, then k square a square. So now what do? I go, this minus goes, I square becomes a minus, then this minus goes, so I have I rho c u0 by k, this I k a becomes plus over there, so it is e to the power of minus I k r dash minus a by r dash, this fellow, then k square a square by 1 plus I k a. Now if omega k is omega by c, then this k goes with that k and I am left with one k on top. This k is omega by c, so I get an omega by c, this c cancels, so I get I rho omega u0, then a square by r square e to the power of minus I k r dash minus a 1 plus I k a. Now if the area of the sphere is 4 pi a square, that multiplied by u0 is the surface volume velocity q. So a square into u0 is q by 4 pi. So I rho omega q wonder why I wrote square over here. This is r only, and it is r dash. This is the r dash, I should copy r dash and r dash. Okay, so q by 4 pi r dash e to the power of minus I k r dash minus a over 1 plus I k. This is the pressure actually at r dash, because it is independent of theta dash and phi dash. Okay. And if we specialize it to a monopole, that means make Ka much smaller than 1, okay, in that limit it becomes I omega rho q by 4 pi r dash e to the power of minus I k r dash. Okay, so it's like a monopole. It's like a monopole. This is a monopole approximation. We have a monopole. This is the pressure generated. The strength of the monopole is still Q. Okay, so that's the answer. This is the answer. This is the response, pressure response when you have a pulsating sphere, a nominal radius a with an oscillation, small oscillation on top of it, and uniform with theta and phi. We will look at this in a lot more detail. Let me just say that using Neumann Green function we have acquired the expression. Okay. Now let us see, we can do this problem using mere expansions that we got from separation of variables. Okay, from separation of variables, if you remember, we got r1 jn of r plus r2 yn of r, or similarly the Hankel functions hn1 and hn2, and multiplied by finally ymn theta phi, which has the Legendre functions from theta and e exponentials from phi. Okay, so we can sum these up and have a solution. That's what we found, right? So let's say if p of r comma theta comma phi comma omega is equal to summation over n summation over m Cmn, okay, let us say function of omega or k, then Hankel function second kind kr ymn theta comma phi for an exterior problem. Okay. Then what happens at the surface? So this is driven by what? This is a solution for a homogeneous problem, so it must be driven by a boundary condition, right? It has to be driven by a boundary condition. Okay. Now if we are looking at again a spherical problem with conditions on a sphere, boundary conditions on a sphere, then we have to provide conditions at r equal to a, right. So at r equal to a, p at r equal to a comma theta comma phi comma omega will be given by n equal to 0 to infinity, m equal to minus n to n, Cmn of omega. Now the Hankel function is at Ka ymn theta comma phi. Okay. Now we know from the orthogonality relation 0 to twice pi, 0 to pi, ymn theta comma phi, okay, ym conjugate n theta comma phi sin theta d theta d phi is equal to delta n n dash delta m n dash, right. Okay. So now if we use that, if we multiply this side and use the orthogonality, okay, so we multiply p by ymn conjugate theta comma phi, okay, then sin theta d theta d phi, and we integrate over 0 to 2 pi and 0 to pi, then I will get on the right hand side my Cmn and Hankel function Ka, because I will do the same thing on this side, multiply by ymn conjugate theta comma phi and then sin theta d phi and integrate, okay, so that n and n dash match, m and m dash match, sorry, this should be m dash, this be n dash, sorry, yeah. So then out of this total sum a single n and a single m will be chosen, so that I will have a single Cmn and a single Hankel function left out, okay. So now my Cmn can be found out, okay. Cmn is this Hankel function that comes beneath over here, okay. So if I now call this entity my Pmn of A, okay, this thing evaluated at A theta phi omega and using the orthogonality relation, this entire term is called Pmna. So then my Cmn, okay, is equal to Pmn of A by Hn of Ka. Okay. So now we are heading towards a problem where the sphere surface velocity is given. So in terms of the surface velocity I will need to know Cmn, okay. Once I know Cmn I can find out Pr theta phi, because Cmn is known, I know Pr, I can find the pressure. So in order to find the Cmn I need to find Pmn from the surface velocity, okay. So now if the surface velocity, if let us say the surface velocity is given, okay, then we can find the W dot r comma theta comma phi given by summation n equal to 0 to infinity, sum equal to m equal to minus n to n, okay, this coefficient at r and the spherical harmonic. Okay, this is the velocity profile at r as a function of theta phi. At a certain radius r as a function of theta and phi, this is the profile, and that can be expanded in this form. Okay, that is expanded in this form. Okay, and what will this w dot look like? The w dot mn at r will look like integral 0 to twice pi integral 0 to pi this w dot at r theta comma phi, the actual velocity on a radius r, at a radius r, into ym conjugate n theta phi and sine theta d phi. That means this has been broken in terms of its spherical harmonics. Okay, this has been broken in terms of its spherical harmonics. That's why you have the spherical harmonic and its coefficient, when summed up, gives you the velocity at a fixed radius r. Okay, now we have the Euler equation. What is that? Del p by del r is equal to minus rho del w dot over del t, which is minus I rho omega w dot is w dot, okay, r theta phi, okay, as a fixed r. Okay, so now del p del r, del p over del r, from here and here, okay, using Cmn value there, how does it look like? It looks like a k in front with a sum over n with a sum over m, p m n of a by Hankel, okay, Hankel function dash kr by Hankel function n of ka y m n theta comma phi. Okay, I have differentiated this expression with respect to r, so Hankel function goes to a derivative. This Cmn I have found from here. Okay, so this now is equal to minus I rho omega w dot r theta phi. Okay, so you see we are going to find the relation between p mn and w dot. Once that is done, this expression is known. Okay, so let's go ahead and do that. So now what happens? W dot r comma theta comma phi is equal to minus 1 by rho c, okay, because this k is omega by c and we have a cancellation, summation over n, summation over m, p m n of a Hankel function dash kr by Hankel function, second kind always Ka y mn theta phi, okay, and this is equal to this over here, this expression over here, summation n summation m w, the coefficients or the spherical harmonics, y m n theta comma phi. Okay, so now this can be written now as w dot mn, because every term is being summed, term by term they are equal, minus 1 by I rho c p mn of A Hankel dash kr by Hankel n of Ka. Okay. So if this is turned into a velocity condition at r equal to A, then we have w dot mn of A is equal to minus 1 by I rho c p mn A Hankel n dash of Ka by Hankel n of Ka. Okay. You see now we have related the coefficients to Pmna. So now my Pmn of A, it is in terms of w dot mn as minus I rho c Hankel n of Ka by Hankel n dash of Ka and w dot mn at A. Okay. So if we write it properly now, P m n of A is minus I rho c Hankel n of Ka by Hankel n dash of Ka. Now this is written in terms of its the original profile at A. These are coefficients of mnth harmonic. What is the totality? Totality is 0 to 2 pi, 0 to pi w dot of A comma theta comma phi, okay, then y m conjugate n theta comma phi sine theta d phi. So this is what w dot mn is from w dot A theta phi. And the total pressure now is as before, I am just repeating, summation over n summation over m p mn of A, which is now in terms of the velocity profile at radius A, by Hankel n of Ka Hankel n of Kr y mn theta comma phi. Okay. So if we substitute this in here, let us do that. Okay. If we substitute this in here, what happens? What happens is we have P r comma theta comma phi at a single omega given by the n sum given by the m sum. Omega is given by P m and A first, okay, which is, let's say here, minus I rho c hn of Ka by hn dash of Ka integral 0 to 2 pi 0 to pi w dot a comma theta comma phi y m conjugate n theta comma phi sin theta d phi, okay, that is PMNA. Then I have one over Hankel function Ka and then Hankel function Kr, okay, and outside is y m n theta phi. So now that there is no confusion here, because theta phi are integrated, I will make them dummy variables. These are dummy variables, theta dash phi dash, so that there is no confusion with this theta phi, because I am looking at pressure at R theta phi, that should remain, and these are dummy variables, okay. So now here I have a cancellation of Hankel and Hankel, okay, so that my P r comma theta comma phi comma omega looks like double sum, I will not write the indices, Hankel function Kr by Hankel dash Ka, okay, minus I rho c integral 0 to 2 pi integral 0 to pi w dot velocity profile at radius a dummy theta dash phi dash y m conjugate n theta dash phi dash sin theta dash d theta dash d phi dash y m n theta phi. Okay, so now let us bring the integrals out. So I have minus I rho c integral 0 to 2 pi integral 0 to pi double sum Hankel n of Kr Hankel n dash of Ka y m conjugate n y conjugate mn theta dash phi dash y m n theta comma phi, okay, then w dot a theta dash phi dash sin theta dash d theta dash d phi dash. Okay. So now what we have here, is integral, we will write it a little differently, 0 to pi summation n summation m Hankel n of Kr Hankel n dash of Ka y m conjugate n theta dash phi dash y mn theta phi minus I rho omega by K a square w dot a theta dash phi dash a square sin theta dash d theta dash d phi dash. Okay, this is the area differential. Let me say d as 0 at a. Okay, so now the pressure is written as integral 0 to 2 pi integral 0 to pi sigma 1 by Ka square Hankel function of Kr, Hankel function Ka y m conjugate n theta dash phi dash y m n theta phi minus I rho omega w dot a theta dash phi dash d s 0 of a. Okay. Now for the exterior radiation, the del n and del r are opposed. Okay. So what I will have here is this is equal to integral 0 to 2 pi integral 0 to pi double sum 1 by Ka square Hankel n of Kr Hankel n dash of Ka ym conjugate n theta dash phi dash ymn theta phi close. Okay. Then negative with del p del n at r equal to a ds0 of a. This is equal to del p del r. Okay, and I put a del p del n, I put an additional minus. Okay, so now this was all p r theta phi omega. Okay, now I replace r with r dash. Okay, r with r dash, theta with theta dash, phi with phi dash. Okay, if I do that, so I have 0 to 2 pi 0 to pi sigma hn kr dash hn dash of Ka, nothing changes here, nothing changes here also. Okay, ym conjugate n theta dash phi dash ymn theta phi minus 1 del p by del n ds0 of a. Okay, it is now on theta phi, theta comma phi. a square sine theta d phi. Okay. Similarly, theta dash are replaced with theta and phi dash are replaced with phi. So that now what do I get? This thing looks, okay, there is a k square missing. This k square is missing. So let me put it here. 1 by k square. Okay. So what I have in here is, if I leave out del p del n ds0a over theta phi coordinates, okay, what I have is minus 1 by ka square Hankel function kr dash, the inquiry point Hankel function dash ka ym conjugate n theta dash phi dash ym theta comma phi, okay, into del p by del n into ds0. Okay. So this is exactly equal to surface integral the Neumann Green function a theta phi, the source, r dash theta dash phi dash, the inquiry point, into del p n by del n, del p by del n, sorry, g del p by del n ds0. So this is the Neumann Green function version of the Kh integral. So we get the same answer. Okay. So now I just wanted to show you that if you started off with the Neumann Green function and you found the solution, it's the same as using the separable variable solutions, and summing them up for a problem where velocity is given, problem where surface velocity is given on a sphere. That's what I wanted to show you. Okay, so I will stop the lecture here. Next class I will show you the same pulsating sphere using boundary matching technique, and then we will look at that solution in a little bit detail, look at how velocities behave in the near field and far field, and get a physical feel for that picture. Close it now. Thanks.